Okay, so last time we talked a little bit about curves. So we talked about like how to maybe find a parameterization and how to sketch some of them. So I'm going to start today by talking a little bit more about curves. So remember that we typically represent curves with a parameterization. So right now I'm just going to make one up. I'll start with something relatively simple. All right. So here I have a parameterization of some curve. So remember, one way to think of this was to think of t as representing time, and then you can think of this as representing like the position of some particle at time t. Okay. Now, with curves, we can do like calculus. So right now, if I wanted to compute the derivative, so you can compute the derivative of such a function just by computing the derivative of each component. All right. So here, the derivative of t would just be 1. Derivative of t squared would be 2t. And then derivative of t cubed would be 3t squared. All right. And so not difficult, right? So what does this derivative vector end up representing? Okay. So if I draw just like a generic picture over here on the side, okay, let's say that this is our curve represented by r of t. Okay. And then let's say I pick a particular point on this curve. All right. Let's say that this is the point at time t0. All right. Okay, so the derivative is going to be a vector which is tangent to the curve at this point. So the derivative vector r prime evaluated at t0. It could look something like this in my picture, all right? Now, if we are thinking of r of t as representing like the position of something at time t, then we could think of the derivative as representing the velocity vector, or just like the velocity at time t. So that's another way of sort of thinking about or trying to visualize what the derivative represents. Okay. The second derivative would then represent, say, acceleration, if you guys remember, right? Okay. All right. So in Calculus 1, a common type of question that you had was to find the equation of a tangent line to a curve at a certain point. So we can do something similar. So remember though that in order to describe a line in higher dimensions, we have to use something like the vector equation or the parametrization. So we might try to write the equation of the tangent line in this form that we did before, all right? So yeah, if you remember, R0 is a point on the line. Whereas V was a direction vector. So let's say if I want the tangent line to my curve, at the point R of T0. So like at this point right here on the curve. So the idea is that our derivative already gives us a tangent vector to the curve. So hence we can use the derivative as our direction vector and use it to write out the parametrization or the vector equation of our tangent line. Okay. And I'll tell you what, so this is not a big deal, but I try to, because we usually use R of t for the parameterization of our curve. So to distinguish, I try to not use R again for my tangent line. It doesn't really matter, I suppose, but I typically use something like L instead for like line. All right, but I do that, oh. Whoa, okay. Did I open up a new? Oh, not sure. Should I go back? Okay, cool. Okay, all right. I was worried that I lost everything. Okay. What was I saying? Yeah, so I'm just gonna use L of t instead of R of t, just to distinguish from our curve. All right. Okay, so then for our tangent line, we could write a formula L of t would be, so the point on the line would be R of t0. And then for our direction vector, we would use the derivative R prime of t0, and then times t. Yeah, okay? Okay. So then just continuing with my example. So if we want to find the equation of the tangent line, at the time t equals 1. Okay. Then we're going to need two things. We're going to need the point on the curve at time t equals 1, and then we need the direction vector at time t equals 1. So we'll plug 1 into the original R of t. Okay. So we plug in 1, you're going to get 1, 1, 1. Then we also need to plug 1 into the derivative. So plug 1 into the derivative, and we're going to get the vector 1, 2, 3. All right, so then writing out the equation of our tangent line. So we're going to have the point 1, 1, 1. And then we're going to need plus t times the direction vector given by the derivative, so 1, 2, 3. Okay. All right, any questions about that? Okay. All right. Let's try and do one more example first. So, yeah, so again, I'm going to write out a parameterization of some curve. Okay. All right, so it's a somewhat more complicated curve. Let's say we want to, again, find the equation of the tangent line. Let's say we want the tangent line at the point 0, 1, 0. Okay? Okay. So in order to get the tangent line at this point, the thing is we need to know like what time t are we going to be at that point. Okay. So what we can do is, let's see here. So what do we need? So we need to find the time t such that our t is going to be equal to this point that we were given. Right. Okay, so that's as simple as just equating the x, the y, and the z components together. All right, so if I do that, then this means that t e to the t has to be equal to 0, comparing the x components. 2t plus 1 squared has to equal 1. And then sine of pi t would have to equal 0. Okay? All right. And then from these equations, and from the first one in particular, you can see that the only possibility would be t equals 0. All right. Okay, so sometimes your equations are more difficult, but the idea is if they give you the point but not the time, then you're going to need to find the time first by solving these equations, solving the system of equations, if you will. All right? Now, the reason why we need to find this time is because we need to know what the tangent vector at this time is going to be in order to get the equation of our tangent line. All right. So now that we know this time, we're going to compute the derivative first. All right. So here, when you're getting the derivative, so you guys want to remember like your derivative rules from calculus. So in this first part, you're going to need to do a product rule, right? Okay. You guys remember the product rule? Okay. All right. If you didn't, I was just gonna tell you to brush up. Okay. So the way I do it is I do derivative of the first times the second plus the first, and then times the derivative of the second. Okay. What about the second term? If I want to get the derivative of this, what would we do? Yeah, okay. Yeah, very good. So bring the power out front, right? decrease it by 1, and then times the derivative of the inside. Good? And then at the end, derivative of sine was cosine, right? Yeah. And then there's a chain rule, so you have to multiply by derivative of the inside. Okay? Okay, good. And then we need the derivative at time 0 to get the tangent vector. Okay? So we're going to plug in 0 and we're going to get 1. It's going to be 4, right? Here, when t is 0, cosine of 0 is 1. So 1 times pi, so it'll be pi. Okay? Alright, good. So now writing out the parameterization of our tangent line. So we have the point 0, 1, 0. We have the point plus t, and then times the tangent vector, which we got from the derivative, is 1, 4, and pi. Okay? Any questions about that? All right, cool. Okay. So we talked a little bit about computing the derivative and what that means, all right? You can also compute the integral. So let's say, just in general, we have some curve r of t, and let's just say the x components are x of t, and the y component y of t, and then z of t for the z component, okay? All right, then if we wanted to integrate this function r of t, okay. So just like with derivatives, we'll integrate this just by integrating each component. So effectively, you'd be doing like 3 integrals, 1 for each of the components, and then your answer in the end would be a vector, right? The vector of these 3 values from the 3 integrals, all right? You guys get that? Okay. I actually think that this is not so important, so I'm actually just not going to do any examples of it, all right? The main thing that you'd want though is to be sure that you're familiar with like basic integration techniques, okay? But I think in the grand scheme of things, integrating functions like this is not super important, so I'm not going to do any examples. What I'm going to touch on next is the notion of Arclength. Okay. So let's say I have some curve. R of t is a parameterization for it. And let's say if I restrict t to some interval ab, all right? Let's say that my curve looks something like this. All right. So perhaps this first point would be r at time A, and this last point would be like r at time B. And what we want to do is we want to compute the length of this segment of the curve, all right? So there is a formula for computing the arc length. Well, formula for arc length. Okay, so you can compute the length of the curve by doing the integral from A to B of the magnitude of the derivative vector, okay, dt, all right? So that will give us the arc length of the curve from A to B, all right? Now, I'll just give a sort of quick idea as like what's going on in the formula, why is it that this actually computes the length, all right? So I don't want to go too far into like a rigorous derivation, but just the idea of how this formula works. So remember that if we're thinking of RT as representing position, then R prime of t is sort of representing the velocity, right? So as a vector, velocity has like two components to it. Its magnitude, which we call the speed, and then the direction. So in particular, the magnitude of the velocity vector gives us the speed that you're traveling at. So in the formula, what you're roughly doing is taking your speed times time, and speed times time gives you like distance, if you will, distance traveled. So that's roughly the idea of this formula, all right? Now I want to do a couple of examples. Okay, so let's look at this example first. So I have some curve r of t equal to 1/2 t squared, 2 root t, and then 1 over 2t. Okay? So for this curve, let's say we want to find the length or arc length. With t between 1 and 4. No, I think 1 and 2 is fine. Okay. All right. So in order to compute the arc length, we have our formula up here. So we need to compute the derivative and then get the magnitude. All right. Okay, so first getting the derivative vector. Okay, who can tell me what the derivative will be? Okay, all right. Next.
1 over t.
Okay, 1 over square root t. All right, and then last. Yeah, okay. 2t squared. All right, good. And we need the magnitude of the derivative vector. And so remember that the magnitude is the square root of like x squared plus y squared plus z squared. Okay. So here, x squared would be t squared. Y squared is going to be 1 over t. And then z squared is going to be 1 over 4 t to the 4th power. All right. Oh, okay. Well, okay, I think my example is broken, but that's okay. Let me fix my example, okay? I guess I made a mistake when I worked it out earlier. So, I want to make this example work. It's going to be kind of awkward. That's okay. So I'm going to change the middle component because otherwise I think my integral is kind of complicated. Maybe you guys already know like what's supposed to happen, right? Okay. So let me think. So in a lot of the Arclength problems, basically the idea is like what you end up with often looks really complicated, right? But usually in your problems, you're able to simplify it pretty nicely. One of the things that often happens is that the inside of your square root becomes a perfect square, so that you'd be able to square root it. Okay. What I have right now is not a perfect square, so I think that's not good. I think if it were to be a perfect square, I should actually have, to get a perfect square, I think I would need this. Okay. Which means my derivative would have to be the square root of that. Which then means that here I would need the antiderivative of that, which would be this. Okay? Alright, so let's just start from the beginning again. So if this is what I have for my parameterization, so we compute the derivatives of each component. Okay? And then we compute the magnitude of the derivative vector. Alright. And then, if I'm not mistaken, then here the inside of the square root will turn out to be a perfect square, alright? So that's probably what I'd be trying to do if I had something really complicated looking like this on the inside. So in particular, I think you can factor it as t plus 1 over 2t squared all squared, right? No, actually, so then that'll give me, oh, wait a second. Oh no, you know what? I think I was correct originally, and I was making a mistake just now. That's my bad. I apologize for this, okay? Maybe I'll like just re-record this portion of my review. That's my bad, so I need to change this again. What we had originally was fine. I'm just not good at doing math in my head, I suppose. But let's just double check to make sure that this does factor as that perfect square, all right? Okay, so let's actually check it. So it's usually easier to work the other way, so let's just take this and square So when we square it, it should be like a squared plus 2 times a times b, and then plus b squared. So that should simplify as t squared plus, this would be 1 over t. Alright, good. Alright. So yeah, I was actually correct before, and then I was just messing up just now. Okay? Alright. Are there any questions so far? Because I know
How did you get that one?
How did I get what?
The t plus 1 over.
This?
Yeah.
So it's the idea that what I'm trying to do is rewrite what I have on the inside as a perfect square. Because I was saying earlier that for these types of problems, you can often expect this to happen, that the inside is a perfect square. So then it's just a matter of actually trying to see how it factors, okay? If you remember how a perfect square works, like a plus b squared, you know, is a squared plus 2ab plus b squared. So if you're trying to determine like what a and b are, what I usually do is I look at what's on the inside and look for 2 terms that happen to be perfect squares. In this case, this one and this one. So the idea is like this is my a squared and this is my b squared. So then therefore my a should be t, and my b should be this. That's kind of the idea, all right? Okay, good. So in this case, yeah, you can simplify that by canceling the square root with the square. All right. So then in the end, in order to get the arc length, so we're going to integrate from 1 to 2. And the formula, we were supposed to integrate the magnitude of the derivative. And we've already computed that, so I'm just going to plug it in. So t plus 1 over 2 t squared dt. And then I guess let's just quickly finish up the integration, all right? So integral of t would be t squared over 2, okay? And then the integral of 1 over 2t squared, so we have to write it as t to the negative 2. And then add 1 and divide, so it'll be negative 1 over 2t, okay? And then from there, I'm just going to plug in the bounds, and that'll be our answer. So we plug in t equals 2, we're going to get 2 minus 1/4. Remember, we subtract what we get when we plug in 1. It would actually be half minus a half, so it's actually 0. Okay? So I guess 2 minus 1/4, if you want to simplify that, should be 7/4. And then that would be our answer. All right, any questions about that? I hope it didn't confuse anyone. But okay, all right. Okay. So with Arclength, the main difficulty is computing the integral. So you should somehow expect the inside of the square root to simplify nicely. Sometimes it's a perfect square. If it involves trig functions, then you might need to do some trig identities in order to simplify it. I have another Arclength problem, but I'm not sure if it's that important, so I think I'm going to move on to another topic instead. Okay? All right. Well, maybe I'll ask you guys a question. Do you guys remember how to do trig substitution in an interval? been a while. Would you like to see an example of that? Okay, all right. I'll do another Arclength problem. I think it's not a big deal. I don't have too much to talk about today, so I can probably do it. Okay, so let's consider this function next. All right, so this curve is going to be sine t, ln t, and then cosine t. Okay. And let's just say we want to find the arc length from, let's do, I don't care too much. Let's go from pi over 4 to pi over 2. Okay? All right, so first we would compute the derivative, okay? So in this case, the derivative would be cosine. Derivative natural log was 1 over t. And then derivative of cosine was negative sine t. All right. So then next, remember that we need the magnitude of the derivative vector. All right, so the derivative, so x squared would be cosine squared plus 1 over t squared. And next we're going to get plus sine squared. Okay? And you guys see any simplification that we can make? All right, what can we do? Yeah, okay. So yeah, remember that cosine squared plus sine squared is equal to 1. This is 1 plus 1 over t squared. Okay? All right. So then in our problem, oh, you know, I guess, yeah, it doesn't matter. Okay. So we're integrating pi over 4. So we're going to be integrating the magnitude of the derivative. So 1 plus 1 over t squared, and then dt. Okay, this makes my balance nicer. So I'm going to change it. Looks like just 1 to 2 would be pretty simple, because I don't have any trig functions in my integral. So I don't need to be doing stuff with pi. Okay. I mean, it's not a big deal, but okay. All right. Now, in order to evaluate this integral, so this time the inside of our square root is not a perfect square, so we're not able to like factor it like we did in the previous example. So I'm just going to start trying to do a little bit of simplification. I think I'm just going to start by getting a common denominator, so putting everything into one fraction. So we should get t squared plus 1 over t squared. Okay? All right, good. All right, so then next, if I want to simplify this a little bit, what can we do here? Any suggestions? So you guys might know that when you square root a fraction, you can square root the numerator and the denominator separately, right? So I'm going to simplify as square root of t squared plus 1 over t. Okay? And now at this point inside the square root, we still have like 1 plus t squared. So in order to evaluate this integral, I'm going to do a trig substitution. Okay. So if you guys remember your trig identities, so we used this identity already, how cosine squared plus sine squared equals 1. Do you guys remember some of the other trig identities, like similar to this one? Okay, so sure, yeah. So there's sort of a trick to getting the other ones. So if you ever like forget them, but you're trying to recall, if you take this equation and if you divide everything by cosine squared, sine over cosine is tangent, so you're going to get 1 plus tangent squared. Yeah, 1 over cosine was secant, so you're going to get secant squared on the other side. Okay? Alright. So the idea is that inside our integral, where we have 1 plus t squared, that looks similar to this trig identity where we have like 1 plus tangent squared. You guys see that? Okay. So that kind of suggests that we're going to try substituting tangent data for t. All right. So that way the inside of our square root is going to simplify nicely with the substitution. Now anytime you're doing a trig sub like this, you do need to compute the derivative as well. So do you guys remember what the derivative of tangent was? Yeah, secant squared. So you guys kind of need to get comfortable with these formulas from before, right? Okay. Secant squared theta, d theta. Okay. So let's see what happens when we make these substitutions into our integral. So inside the square root, we get 1 plus tangent squared, which will be secant squared. All right? So you're going to have square root of secant squared, which would just be secant theta. Dividing by t, so we have to substitute tangent theta for t. And then dt, we also need to substitute that. dt is secant squared theta d theta. All right? Is everyone good with that?
Why did you set t with tangent theta?
Because that was going to simplify my inside of my square root. Okay. Because if t is tangent, then we get 1 plus tangent squared, which we know is secant squared. Okay. Okay. So then what we're still left with is evaluating this integral. Okay. All right. So in order to evaluate this integral, there's maybe a couple different trig identities that you can try to use. I think what I'm going to try and do is I'm going to try to write a couple of things in terms of sines and cosines. All right. So in particular, remember that tangent is sine over cosine, right? So if I'm dividing by tangent, I can multiply by the reciprocal. So I can multiply by cosine over sine. And then I still have the secant squared theta, d theta. Okay. So I was just thinking that we can cancel the secant with the cosine if I do that. Secant is 1 over cosine, all right? All right, so next we have secant squared theta over sine theta. Okay, so let's try and use maybe this trig identity to rewrite secant squared. Okay. So let's try writing it as 1 plus tangent squared theta over sine theta. Okay. Okay, so I think this will work. So I guess I'm going to split this into 2. So I'm going to rewrite 1 over sine as cosecant. Okay. And then let's look at the tangent squared over sine. So what I'm going to do for that one is I'm going to rewrite tangent as sine squared over cosine squared. And that was divided by sine, so actually I'm going to put the 1 over sine on the outside. Okay? So then here I can cancel out another sine, top and bottom. Is everyone good so far with what I'm doing? Okay. And so I think we're left at a point where we can evaluate our 2 integrals. So integral cosecant, and then here we have sine over cosine squared. All right, good. So the integral cosecant theta. Okay, so maybe you guys don't remember the formula for that, but it was negative natural log cosecant theta plus cotangent theta. Okay? All right. For this second integral, okay. So for the second integral, so you guys might see that you can do the U substitution, which is what I was thinking initially, but I also see that I can rewrite it as sine over cosine, which is tangent, times 1 over cosine, which is secant. Okay. So I think that's going to be a little bit nicer, because remember that the antiderivative of this would be secant theta. Okay. All right, is everyone good with that? All right. So now we've evaluated our integral. Okay, so let's go back to what we had. So first, we need to switch everything back to the original variable t. All right? Do you guys remember how you would do this?
You drove the
Yeah, very good, yes, okay. Yeah, so we usually did this by drawing a triangle. So I'm going to draw a right triangle right now. And I'm going to label one of the angles as theta. Okay? Now the original trig substitution that we did was t equals tangent theta. So tangent theta was t. I'm going to write it as t over 1. And the reason why I'm doing that is because I'm thinking in terms of a right triangle, how tangent is like the opposite over the adjacent. Okay. So what I'm going to do in my right triangle is I'm going to label the opposite side as t, the adjacent side as 1. And then what we can do right now is calculate the length of the hypotenuse using the Pythagorean theorem. So the length would be the square root of a squared plus b squared, so it would be 1 plus t squared. Okay? Alright. So then the idea is we'll use the right triangle to figure out what cosecant theta and what cotangent theta and secant theta are going to be. Alright? Okay. Okay, so cosecant is the reciprocal of sine, so it should be the hypotenuse over the opposite, right? Alright. So the hypotenuse is the square root of 1 plus t squared. And then the opposite is t. Okay? Alright. For cotangent, it would be the adjacent over the opposite, should be 1 over t. And then secant would be hypotenuse over adjacent, which would just be 1 plus t squared over 1. Alright? Okay. So that's everything written in terms of t. So then the last thing that we'll do is, in order to get the arc length, we needed to plug in our bounds from 1 to 2. Alright? And so I'm going to set that up. Arc length would be negative ln root 1 plus t squared over t plus 1 over t and plus square root of 1 plus t squared. And then we need to plug in the bounds 1 and 2. Okay? Alright, so at this point, you guys can plug in the numbers, right? And subtract. Alright. So let's wrap up this example at this point then, okay? So the rest of it is just plugging in numbers and whatnot. So I'm
Can you tell us the final answer?
I do not know the final answer, but I'll always plug in the numbers and get it, yeah, okay. Alright, so any questions or any other questions? Okay, so the last thing that I wanted to talk about today was just drawing contour maps. Alright, so drawing contour maps sort of amounts to drawing a bunch of level curves. It's basically all it is. All right. So I wanted to do maybe just a couple of examples. I'll point out a couple of details about contour maps as I'm doing my examples. All right. All right. So let me start with the following function. F of xy equal to okay, I have a couple of options. I'm just going to go with ln. Let's go with this one first. Okay. So for this function here, we want to sketch some of the level curves. And then we're going to put all the level curves into like one graph or one plot. And that will kind of be our contour map. Okay. Yeah, so what we need to do is sketch some of the level curves. All right, so do you guys remember how to get level curves again? What do we do?
Do you set the variable equal to t?
You're sort of close, maybe. So remember that level curves we get by setting our function equal to a constant. So if you think of the function as representing the z-coordinate, right? So we're plugging in different values of z to see what's happening at different heights, different levels. That was kind of the idea of level curves, all right? So for now, let me just, before I plug in any specific numbers, I just want to just plug in something generic right now, okay? So just imagine that I plug in some constant c for my function. So then we'd end up with this equation, ln of 1/2 x plus y equal to constant c. All right, so what kind of curve does this look like in the xy plane? Any idea? Okay. Well, it looks kind of complicated because I have like ln and all that stuff, right? So let me do one thing first. Let's get rid of the ln. If I wanted to get rid of the ln, what would I have to do? Yeah, e or exponentiate both sides, however you say it. So yeah, if I apply e to both sides, we'll get 1/2 x plus y equal to e to the c, right? Can you guys tell from that second equation what this will look like? So remember, e to the c is basically like some constant, right? So they give it as a constant, what would this be? Yeah, so let's see here. Let's just move the 1/2 x over, so it's like y equals negative 1/2 x plus constant. And so you guys maybe recognize this is the equation of a line, isn't it? So the slope is like negative 1/2. So the c is affecting what the y-intercept would be, right? Okay. Okay, so yeah, in this example, we can see that the level curves are going to be lines. If you will, all right. Now, let's plot just a few specific level curves right now. Let's look at what happens when c is equal to 0. Let's do that first. So when c equals 0, this equation will become y equals -1/2 x plus e to the 0 would be 1, okay? So if I'm trying to sketch this line in my picture, so the y-intercept is at 1, and the slope is -1/2, so I'll go down 1 and over 2. Alright, so the first level curve that I have looks something like this. So this is at the height c equal to 0 or z equal to 0. Okay? Let's do just a couple more for now, okay? So let's just go out to say that c equals 1. So at c equals 1, I get a different line. It's going to be y equals -1/2 x plus, this time we have plus e to the 1, so plus e. Okay? So e is about 2.7, so we're going to be maybe here or so. Just kind of guess. And it has the same slopes as the previous line, so it's going to be parallel to it. Okay? So this would be at a height of z equals 1. And maybe just like one more, so you know what happens if we plug in c equals 2? Then the y-intercept becomes e squared. Okay? So e is 3-ish or so. E squared is close to 9 then, right? So it's going to be sort of like way up here somewhere now. Okay? Alright, now it has the same slope again, so it should be parallel to the previous lines. This is at a height of z equals 2. Alright, and so then at this point I'm going to stop for a moment. Okay, so the idea is if we were to draw a bunch more level curves, alright, you can try to get an idea as to what the graph of our function looks like. So what you want to pay attention to is like at what height or at what level are all of these curves at, okay? If I were to try to sketch the graph right now, just based off a little of what we've seen, a sketch of graph. So this would be a rough sketch, all right? Okay, so basically, in the xy plane where z is equal to 0, okay, we should have this line as part of our graph. So I guess in my picture it might look something like this in the xy plane, right? Okay. So then at the height of z equals 1, so we're also going to have this line, but so basically I want to take this line and basically I want to sort of lift it up to a height of 1 unit, all right? So my second line should be like a little bit further out this way. but I need it to be lifted up to the height of 1 unit. So I'm going to try and draw a good picture. Yeah, it's not super great, but okay. So the second line is supposed to be 1 height above the xy plane, all right? This third line, which is a bit like further out here in the xy plane, but it should be lifted up to a height of z equals 2, all right? So at this second height level, you know what, let's try to draw a better picture. At this height, I should have the line parallel to the ones beforehand. That's a little bit better. So it's at the height z equals 2. Let me try to fix what I have so far. Okay. So here's the first level curve that I have in the xy plane where z is 0. Okay. So the next line that I draw should be at the height of z equals 1. So I'm going to have to exaggerate a little bit. So here is the second line that we drew in our contour plot. But imagine that being at the height z equals 1. I don't think I need this anymore. And then yeah, finally at the height of z equals 2. We have this third line, which I'm going to just sort of try to draw this way. So it looks a little bit curvy perhaps, but pretend that it's a straight line. Okay? So you can sort of imagine connecting these lines, so it's kind of sloping up as you go out. Okay? So I get sort of like a ramp sort of figure, I guess, opening up like that. Okay. So that's like a really rough sketch of what the graph kind of looks like based off what I'm seeing in the contour plot. All right. So do you guys get how I'm using the contour plot in order to sketch the graph? Okay. Okay. Now right now, the contour plot that we drew only has 3 lines on it, right? Only 3 level curves. So that doesn't really give you like a super great picture of the graph. So if you want to get like a better picture, you might try to draw like a lot more level curves. Okay. Now here, just sort of like a sort of convention that we have when we're drawing level curves, or when we're drawing contour maps in general. Okay, so in contour maps, what we try and do is we draw level curves like more closely bunched to each other when the graph is like really steep, meaning it's like changing very rapidly. Okay. So we draw level curves more closely together when the graph is steep. So it's like changing rapidly in slope or in height, if you will, all right? So as an example, if I draw 2 examples of contour maps right now. So let's say that you're given one contour map which looks like this. And then let's say I'm given another contour map which is very similar, but it's going to look like this. Oops. Okay. So I wasn't so quick at drawing my circles, but my intention is that in this first picture, the circles are kind of like evenly spaced out. My intention for the second picture was that, yeah, it's not drawn too well, but my intention was that they're getting closer to each other as you go further out. That was my intention, okay? Okay. So let's suppose that in this first picture, let's say this first curve was at the height z equals 0. Yeah, well, that's fine. Let's do z equals 1. Let's say the second circle is at the height of z equals 2. And then the last one is at the height of z equals 3. All right? So if I were to try and draw a picture of what this curve, or sorry, what this graph might look like from the contour map. So what we're saying is, like, at the height of z equals 1, we have this small circle. So imagine this circle being raised up at the height of z equals 1. At the height of z equals 2, we have that second circle, kind of like this. And then, like, at the height of z equals 3, we have that third circle. This. Okay. So what kind of figure do you think this will look like? Oh yeah, it could be a paraboloid. What else could it be? Cone, alright. And then in the second one, it will look kind of similar as well, right? So my intention was that one of these was supposed to be more of a cone, and one of them was supposed to be more of a paraboloid. Okay? So how to maybe just tell or distinguish these two apart from each other? So the key was what I tried to do in my contour map, where I tried to make these circles like evenly spaced. Whereas in this contour map, I was trying to draw the circles on the outside like more closely bunched to each other. Okay. So the key is, like, if you're thinking about what I said up here earlier, so contour maps, when level curves are more closely bunched to each other, that indicates that your graph or your surface is more steep. So it's like changing more rapidly. All right. So with that idea in mind, which of these two is more likely to be the cone, and which one's more likely to be the paraboloid? What do you think? You first. Which one?
The cone is the one in the right.
On the right? Okay. What do you think?
Cones on the left.
Cones on the left. Do you have any opinion?
I think on the right.
On the right. Okay. So to me, the cone is going to be the one on the left. All right. Because remember that the cone like rises at sort of like a constant pace. Oh. So that will be reflected in how the circles are like evenly spaced out. All right. For the paraboloid, so remember that the paraboloid, it kind of shoots up a bit more quickly. So the idea is like when you're looking at the paraboloid, when you go further out, it gets more steep, right? It gets more like vertical and steep. So that's why the level curves for the paraboloid would be more closely bunched together as you go further out, because it's getting steeper up there. Okay? Alright, so do you guys understand that property of contour maps? Okay. Yeah, so when you're reading a contour map, pay attention to like, I guess like the density or like how bunched together the level curves are. That gives you a better sense for how steep the graph is supposed to look like, all right? Okay. Any questions? Okay, all right. So then like, if you wanted to, then going back to this previous example, you might try to draw a couple more level curves. Try to bunch them together where it seems that the graph is getting more steep. But I think I'll wrap things up with that, okay? All right.